Hey everybody, this is Mrs. Nickel. Um, Reminder, this your review assignment from the last couple days is due on Monday, and your Chapter 1 test is on Monday. All right, so today you're going to learn about transformations of quadratic functions. We're going to fill out our little half sheet about the parent function for a quadratic, and then we'll do some examples of how you describe and graph quadratics. This is Chapter 2, Section 1. All right, so first of all, you should have one of these half sheets. I asked Mr. Carlson to pass these out before you started. We're going to fill this out for a quadratic function. So bear with me because I've got to use a mouse to write today. So my handwriting might not be the best. Okay, the name of this family is the quadratic family. The function, the parent function, the bare bones quadratic function is just x squared. And sometimes you'll see f of x equals x squared or y equals x squared. Okay, our key points, we're going to make our table and then graph those. So inputs, these are x values. We've got -2, -1, 0, 1, and 2. My outputs, or y, you can put y in that spot too. -2 squared, that's -2 times -2. We're looking at 4. -1 squared, +1, 0 squared, 0. 1 times 1, 1, 2 times 2, 4. All right, so remember when you square a negative number, its output is positive. Let's go ahead and graph these. 0, 0, 1, 1, 2, 4. Oops, I just put that in the wrong spot. Don't do what I did. All right, we could do 3 and -3 to just fill in this graph a little more. So that would be 9 and 9. Boom. Okay, so ignore that point that's there. Sorry. All right, let's go ahead and sketch this. The shape of this graph is a parabola. That's the name. And the key points are your vertex at 0, 0, 1, 1, -1, 1, 2, 4, -2, 4, 3, 9, -3, 9. Those are those red dots that I just put are key points, and they're going to help us transfer transform the parent function later. We're going to use those to help us when we have to shift this thing right or left. Each of these points will just move right however many, or left however many, or up however many. But I always like to think, here's my vertex, and the first key point is 1 over, 1 up from there. And to the left, left 1, up 1. And then my other key point from the vertex at 0, 0 is right 2, up 4. And then from this vertex, left 2, up 4. Those are the key points I use a lot when I'm sketching a graph for a quadratic function. And we'll get to that more in a little bit. But again, the shape of this is called a parabola. The function family is called quadratic. But the shape of this graph is a parabola. Um, Vertex, that is that minimum point, or it could be a maximum. If the parabola is reflected, then that becomes a maximum. All right, domain. So every single x value, if you looked at a table in your graphing calculator for this function, every single x value would be represented. So we're going to say all x values. Range. For this parent function, the range is all y values greater than and including or equal to 0. It's all these y values above 0. If we were to reflect this parabola, then the range would be all y values less than or equal to 0. End behavior, remember this is how the left and right side of your graph ends. Goes up on the left, goes up on the right. Symmetry, yes, a parabola does have symmetry It is around, I'm going to use a blue line here. For this particular parabola, for the parent function, our symmetry is the y-axis, but for any parabola, the line of symmetry is at the equation x equals and then some number, where this number is the x value of the vertex. And we will talk more about that later. So, for example, right now this parabola is at 0, 0, so my line of symmetry is x equals 0. But if I were to move it over 2, then my line of symmetry would be x equals 2. Asymptotes, we're not talking about that. X-intercepts, for this one, we're at 0, 0, but if you start moving this thing around, you could have no x-intercepts. If it's above the x-axis, you could have 2 x-intercepts if you were to like move it down below the x-axis. For the parent function, our x-intercept 0, 0. Same thing with y-intercept. And transformational form for a quadratic. That's your a value. That's your vertical stretches and shrinks. That's our h value. So if it's inside the parentheses before we square it, that'll shift your graph left and right. And it's opposite of what you'd think, just like with absolute value functions. So if this is x minus 2, inside the parentheses, my graph shifts right 2. And then we have our k value that shifts our parabolas up and down. Um, Other stuff, not that I can think of right now. We already talked about the name of the shape is a parabola and the vertex, and then the line of symmetry going through that vertex. Okay. Boom. So there is your parent function sheet for a quadratic. Remember, these red points are the key points that I'm going to be referring to in these upcoming examples. All right, so we're now going to move on to how do we transform these things around, and how can we do that without using our graphing calculator. So we're going to be manually graphing today. Um, One thing, if you'd like, you could tear out page 26 and 27 from your student journal, and those have visuals for you of the transformation. So reflections over the x-axis, reflection over the y-axis, ups, downs, left, rights, and horizontal, or excuse me, vertical shrinks and stretches. Those pages do include horizontal shrinks and stretches. We will not be covering those today, but they're nice visuals. You could stick them in your notes to help you visualize things. So pause for a minute, go get your student journal, tear out page 26, 27, look through those, take a minute, look through those pictures, and then put them in your notes, and then continue watching. All right, so I kind of already talked about some of this when we were looking at our parent function sheet, but if we move a quadratic function up, these are just examples. Remember, function notation for any function, you add a number to the function. Same thing with the quadratic. If I have x squared plus 5, that's going to move the parabola up 5. Down, general function notation for any function. I subtract a number from my function. So with the quadratic, a basic example might look something like this. That would move my parabola down 3. Left. So let's look at function notation for any function. If you want to move it left, you add something to your x value inside the function. So with a quadratic, that would look like maybe x plus 2 and then squared. That would move our quadratic left 2. It's opposite of what you'd think. General function notation to move something right, any function right, is that for a quadratic, you'll have an x minus some value inside. So that would move our function right 4. Vertical stretch. That is multiplying a function by a value, an entire function by a value. Um, for a quadratic, that could look like, um, I'll go like this. So this would be a quadratic that has been shifted left 1 and then vertically stretched by a factor of 3. Vertical shrink, same idea, but your a value is less than 1, or yeah, between 0 and 1, um, but less than 1. So that might look like this. Boom. That would vertically shrink. That means it widens. All of those y values decrease by a factor of 3. Reflect over the x-axis. That's the negative outside the function. So just real general, look like this. Negative x squared. Reflect over the y-axis. Sometimes it's hard to see with the quadratic because quadratics are a lot of times centered around the origin. So when you reflect it over the y-axis, it looks exactly the same as when you started. So if you were to graph this guy with the negative inside, so if you put y1 equals the parentheses negative x parentheses squared in your calculator, it's going to look exactly the same as just the parent function. Because when you reflect it over the y-axis and it's centered on the y-axis, it won't look any different. Um, so, but the idea is if that negative is inside, it's a reflection over the y-axis. All right. So those are general examples, pretty simple examples, and I also referred to this general function notation that we learned with lines and absolute values. So let's go ahead and do our first few examples. So I started with some easier examples. So we've got x squared minus 2 is our function. We need to describe it and graph it. Well, it's minus 2. It's outside of the x squared, so that would be down 2. When I graph it, here's where I'm going to refer to those key points. I'm going to make them red like we had in our parent function thing. Boom. Full screen. Okay, so here's my parent function points. I've got 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. Those are the key points on the parent function. When I want to graph it and move them all down 2, I'm going to use another color. This is annoying. I have to flip back and forth. That's okay. All right, when I want to move all those down 2, I'm just going to take those key points in the parent function and move them all down 2. So that's these blue points that you're seeing. I'm counting the boxes, 1, 2, 1, 2. They all just move straight down 2. And then I can go ahead and sketch in my function. This should look curved, by the way. Please do not have your parabolas look like absolute values with a V. I should see some curves going on. And there we go. So we've got, in red is our parent function. Those are the key points. But in blue is x squared minus 2. We did that pretty quickly. I didn't have to pull out my graphing calculator. Done. Description, graph. All right, next one. Notice we've got x plus 1 and it's inside the parentheses. It's inside the function. It's before we're squaring it. This would be a transformation left 1. Oops, left 1. Okay, in red are my key points again, 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. That's from the parent function graph, but we're going to move those all left 1. Boom, 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 boom. And now I'm going to connect all my blue points. Oops. Remember, I'm doing this with a mouse, so no judgment. Vertex is at negative 1, 0. And then we've got our function. We haven't transformed it vertically, so it hasn't gotten skinnier or fatter. It's still the same um, width as it was as the parent function. All we did was shift it left. And notice my line of symmetry is now at x equals negative 1. Okay. All right. Next. All right. So now this correlates with, I told you when you see red examples like this also correlates. There's a similar example in your textbook, Chapter 2, Section 1, Example 1 in your textbook. You'll be able to find another example like the one I'm doing now. So this one, it says describe the transformation and then graph it. Well, we've got two things going on here. So let's describe it. Inside the parentheses, I've got a minus 1. That's going to move it right 1. The plus 2, up 2. Okay, so there's my description. Now let's graph it. Again, I'm going to start with my parent, or my key points, 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. And then I'm going to do what my description says. I'm going to move each of those right 1 and up 2. Right 1, up 2. Right 1, up 2. Right 1, up 2. Try to use two different colors because it starts getting, you kind of get yourself messed up and confused sometimes when you use all the same color because you forget which points were your main points and which points were your transformed ones. Oh, it's hard to draw with a mouse, but there we go. There is our transformed from our parent function parabola. We described it, we graphed it. The graphing goes pretty easy if you start with those key points from the parent function. All right, let's do this. So now these examples are going to be our vertical stretches and vertical shrinks. Um, all right, so describe the transformation of the parent function, represented by h, and then graph it. So we've got two things going on here. It is a reflection over the x-axis. Oops, sorry, can't spell. Reflect over x-axis. It's hard to write with a mouse. And we've got a vertical stretch by a factor of 3. Okay, so I'm going to start with my key points. 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. Oh, I should change the scale. That's all right. I'll leave it for now. But know that you can always kind of change your scale how you need. But let's think about this. If I take 0 and multiply by a factor of 3, it's still going to be at 0. So this point doesn't change. Oops, I'm going to go to blue. That's my transformed. I'm going to use blue for the vertical stretch of 3 first. Then I'm going to reflect all the points. So this distance from the x-axis is 1. If I multiply that by a factor of 3, because I'm vertically stretching this 3, 1 times 3 is 3. So it's going up 3 boxes instead of 1. This distance is 1. This vertical distance from the x-axis is 1. 1 times 3 is 3. So it goes to 3. This vertical distance is 4 up. 4 times 3 is 12. But that's what I'm saying. 12 is not on here. So it's like double. My graph ends at 6. This goes to double that. So I'm going to kind of estimate, I don't know, somewhere up there. This side, it's symmetric. So same thing. This one, way up there. But now we've got to reflect it. So I'm going to reflect all these. 0, 0 stays there. This point, so now I'll use green, is the reflection of these blue vertical stretch points. 0, 0 stays there. And then I've got my 12s, which are like way down here, we said. Boom. And then I sketch my graph in. Woo, oh gosh. That was horrible. Sorry. But you get the idea. So I think if you have a vertical stretch and a reflection, I would first do my vertical stretch and multiplied all those vertical distances by 3 from my key points, and then I reflected them over the x-axis. So there's our new function. All right. I had to go pick up my daughter from gymnastics, so I had to pause it and restart. All right, so what did we just do? Okay, so we reflected over the x-axis and did the vertical stretch by 3, and I said to do your vertical stretches. If there was a shift in here, I would do the vertical stretch, I would do the shift, and then I would reflect it over the x-axis at the end. All right, so next example, I should have started with this one. This one's actually easier. Okay, so we're multiplying x squared by a half, so that is a vertical, oh gosh, shrink by a factor of a half. So all our vertical distance are going to go down by a half. So let me make this full. Okay, so with red, I've got my key points from the parent function 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. And in blue, I'm going to take all the vertical distances and graph them at half of what they were. So this one was 4 up, so now it will move to 2 up. This one was 1 up, so now it'll move to half. 0, half of 0 is still 0. Half of this distance height is 1. Half of this height of 4 is 2. And so now my function, and I don't know if you remember, but when we did 3 in the parent function, 3 squared was 9, so that's up here. We could graph this one on this graph. So half of 9 is 4.5. So I can see those points. If I can, I like putting a few more points because then I can draw my parabola a little more exact. Alright, so there's our parabola. It has widened, and that is the vertical shrink because all those vertical distances are changing. They're going up higher or down lower. So the vertical shrink by a half. Alright, so these examples, this example was, we had 2 translations. These were just one of each translation. These are our vertical stretches and shrinks. And our last example, describe the transformation of the graph, the parent quadratic function, and then identify the vertex. So we've got a lot going on here. A vertical stretch by 3, a shift left 2, and then a shift up 1. I like, when I describe these, I like to start inside and work my way out. So first, inside the parentheses, I've got left 2. That's this part. Then I've got, now I'm expanding it out to here. Now I've got my vertical stretch by a factor of 3. I'm going to abbreviate because I can't stand writing with the mouse. Vertical stretch by 3. And then finally, up 1. So this is kind of a visualization thing. Could you plug this into your graphing calculator and then look and see where the vertex is? Yes. But I'd rather you understand what these transformations do to the vertex. So if you imagine on the parent function, we're at 0, 0. I move that left 2. So now I'm at negative 2, 0 for my vertex of my quadratic. We vertically stretch it by 3. Well, the distance from this x-axis, so right here was my parent function vertex. It's at 0, 0. I move my parabola left 2. This vertical distance is at 0. So if I stretch it by 3, it's still at 0. So the vertical stretch will not change my vertex in this example. And then I go up 1. So here's where my vertex is now. So identify the vertex, negative 2, 1. I included 3 problems in your assignment like this. Notice you don't have to graph it. You can kind of do a little thing like I did over here to the right where I put my parent function vertex and then thought about where it went. You can do that if it helps you visualize where the new vertex is, but you don't have to graph it. But you do need to list your transformations and then tell me where is that vertex. So left 2, vertical stretch by 3, up 1, new vertex is at negative 2, 1. And you are more than welcome to graph this on your graphing calculator and check your answer. Alright, so here's your assignment. Mr. Carlson was supposed to pass out some graph paper. The bold problem, so 4 through 12 even, 17, 19, 20, 24, need to be graphed. And yep, this assignment is due Monday with your review. remember I did post problems 3 and 4 from page 34 from the review. I posted those on Google Classroom, worked out the way I would work them out. So feel free to check those out. And I will see you on Monday. Be ready for your test. We're going to start when you walk in. All right. Have a good weekend. See ya.